So, I think I'd like to get started. A very good afternoon, and welcome to the one seminar here. Today, it is my pleasure to invite our speaker, Professor Graham-Brady from Johns Hopkins University. Professor Brady is currently a professor of civil engineering and mechanical engineering at Johns Hopkins. She obtained her PhD from Princeton, and her research interests include computational stochastic mechanics, multi-scale modeling of materials with random microstructures, and the behavior of materials and high rate loading. Professor Graham-Brady has a number of awards. She's a recipient of the Presidential Early Career Awards for Scientists and Engineers, Huber Research Prize from ASCE. So she did a lot of work related to this topic, and without further ado, let us welcome Professor Brady.
Here are a few examples, some sort of, unfortunately, far too close to home. Places where there was significant failure that really started typically from some small localization. So these localizations, when we think down at that small scale, they're typically driven by the local microstructure. And so the question I'm trying to think about is, what is that connection between the local microstructure and those localizations? This is actually a model of, this is actually an experiment, of alumina under spherical impact, and a numerical model that I actually worked on with Dr. Deacon, who shared the graphic with me. And we were looking at localization of damage, and we're sort of happy to see something that kind of looked like the experiment. We won't talk about all the quantitative side of things, but it seemed somewhat promising. So the conceptual approach here is thinking about multi-scale modeling, but a hierarchical kind of approach. And what I mean by that is you think about a large-scale model, and at each integration point, say, if this was a finite element model, you're evaluating a constitutive relationship. So in other words, given a strain increment that this larger scale model predicts at this point, calculate the damage or plastic strain or stress increment associated with that. And this here depends intimately or often on the underlying microstructure. So the microstructure associated with that point. That could be in a brittle material, something like thinking about the number of cracks associated with this little region, the sizes of those cracks. Talking about a metallic microstructure or polycrystalline microstructure, maybe it's grain sizes and shapes of grain boundaries. But the local microstructure feeds into each of these elements, and that's the problem that we're considering. So I guess the first question I'll throw out there that you might ask is, well, how much variability is there really? And so we just did a quick study with a simple 2D damage model. So the damage omega here is just basically the arithmetic average over the number of cracks times, well, this is an area density of cracks, times the length of crack squared. So you can think of it as like a mean square of crack length. And we plotted just simple numerical simulation, what this damage would be as a function of the number of samples. So on the x-axis, we have a number of samples. On the y-axis, we have damage. And these are just different generated samples of damage. And you can see that what you would expect if we went out to an infinite number of cracks in a particular region, then of course the damage is a scalar or deterministic value. If we go to a very small number of samples, there's a high degree of scatter. But what we asked was, when does this happen? When do we not have to go to infinity? We said, well, we should think about when are the variations in damage less than the round-off error. And it turns out that happens when the number of cracks in the sample is about 10 to the 32nd. So then we did a quick little analysis. Well, how many cracks per unit area, think of this as a 2D slice maybe of material, do we see in the ceramic? And it turns out this corresponds to a finite element size of thousands of square kilometers. So, okay. So if you want to say that down to round off here, we don't care about these variations, then you have to be prepared to say your finite element model is such as discretizing units of kilometers. Now, the question is, that variation is real, but does it matter? So yes, the variation exists, but is it important? So I show a couple of examples. Rebecca Brannon at the University of Utah spent a sabbatical out at Hopkins and worked with me last spring, and we had loads of fun. If you know her, she's fiery. And so we just had all sorts of great conversations, but she shared a lot of these model results with me as we were talking about this. And on the left-hand side, you can see there's axisymmetric compression, where here the model assumed that the material is completely homogeneous. So from one element to another, there was no variability in properties. And on the right-hand side, she introduced some scale-dependent variability. So for each element, including some scatter in the properties. And these are the associated experimental results. And you can see that even qualitatively, this is garbage. And this actually gives something much more reflective of reality. Another example we had was spherical impact. And I have another example of this at the end of the talk that I'll show you. You can see on the left-hand side, this is assuming a homogeneous material. This is incorporating scatter, so basically a fuzzy failure threshold, so putting uncertainty in material properties. And this is the experiment here, so you can see this sort of cylindrical sample being impacted by a sphere. From above, this is what the crack pattern looks like from the experiment. Over here, this just kind of seems to suggest that maybe the whole thing pulverizes or something. The yellow indicates damage. But over here, you can see that as you get to a fine enough mesh, you capture some of that radial cracking. So we're getting qualitatively better results. So this not only reflects the fact that if you had two different samples of not only the same material, they might not behave the same, which is one issue that we need to think about in variability. But even if you weren't worried about that sample-to-sample variability, the deterministic or non-random homogeneous model will not give you a physically reasonable result in all cases. So you really do have to think about this. It's an inconvenient truth. So again, going back to my conceptual model. So what do we do? Here's this little element that we can think of. Well, we can go down to that element and generate a microstructure that's associated with that element that has some cracks, pre-existing cracks in it. We can model the crack growth. This is a cohesive zone element model that we did looking at ceramic material. So for each element, you generate this microstructure sample representing each crack. And do that at every load step, at every point. So keep in mind, about a centimeter cubed of a typical ceramic contains about 10 to 6 cracks. But this is going to get out of control pretty quickly. So we have to do something a little more clever than that. We can't just say, well, we have to model all the cracks. We have to incorporate some parameterization that makes this more reasonable. So instead, we're going to represent this microstructure by the key parameters that drive response. And we'll have to decide what we represent and what we don't. We would like to sample as little as possible. And we would also like our micromechanics to be as simple as possible. So our subscale modeling here, we like to simplify. So I kind of covered the first two already. I think I've tried to be general, but specifically what I'll talk about today is associated with dynamic brittle failure. And I'll introduce first the basics of a micromechanics model, skipping over a lot of the details, forgive me for that, and actually trying to present the simplest version of that basic micromechanics model, knowing that there are other extensions and more complex versions of it that are out there, but just to get the idea across. And then show this model as being applied to a model material that we developed, an air-entrained mortar. that we did some dynamic tests and compared resulting strengths to our model predictions, and then finally some ways that we can make this process more efficient, and that's our path forward. So I just like the look of this. It's a photography that came out of the Netherlands, and I just thought it captures exactly brittle dynamic failure. I think the photographer cheated, and he gave me permission to use this, by the way. If you look here, I think he notched the head so he'd have that dramatic like head popping off. But in upscaling for impact, we go back to this figure that's looking at the crack patterns. The microstructure drives those constitutive properties, and our question really is the how. And so that's what this micromechanics model is all about. So in brittle materials, typically pre-existing flaws are driving the failure. So what do I mean by pre-existing flaws? They could be, I'm doing a lot with ceramics, although you'll see I have a cementitious material application here, but you can think of pores, soft inclusions. We have this problem with these graphitic, they call them potato chip defects because they're shaped like a potato chip, but they're this soft, sort of crumbly, chalky material. They're very problematic for us. They could be grain boundaries or pre-existing cracks. In metallic materials, might be triple junctions. In ceramics, we aren't so worried about those, we don't think. So just we'll say there are some pre-existing flaws, and we'll describe them by some simple geometry. So our driving mechanism here is we're going to look at specifically compression. And maybe this will be intuitive to all of you, but it took me a little while to absorb this idea that you would get mode 1 cracking under compression. It seemed weird. So the idea is that, think about this. This is just a 2D model. So it's a conceptualization. In reality, you could think of like a penny-shaped kind of flaw acting somehow similar. But you have a slit-like flaw at an angle with respect to the maximum compressive load. So you'll have a sliding. The top surface under this compressive load wants to slide this way. The bottom surface wants to slide this way. And you create a mode 1 crack growth in the axial direction, in the direction of the maximum compressive load. And this leads to something that's referred to as axial splitting. So as you load it in a particular direction, you get this axial splitting mode. And that's the mechanism that I'll focus on here in the model. So the fundamental concept is what we call this wing crack, which is associated with that axial splitting mode. So this is a test we did. I promised you this model material, this air-entrained mortar, which is not necessarily a material that's useful for any real application that we figured out, but it was useful for us to study. And I just wanted to point out here, this is a Kolsky bar test. You can see the stress versus time. So you see the stress builds up to a peak level, and then you have this characteristic sort of strain softening that happens. This plateau here is weird. We don't know what that's all about. It might just be experimental error. We're not sure. But each of these points that are numbered here are shown, high-speed photos shown down here. And what I want to point to, it's always hard in a projector to see it. Maybe you can. But there is, you can see this sort of axial splitting mode that's occurring, this sort of through cracks in the direction of the loading. I should have made it clear. The loading is a compressive load this way. So typical stress-strain response, just cartoon version of that same thing, is that there's an elastic phase that, stress grows approximately linearly with strain. Then you hit a point with crack initiation and growth, and you see a degradation in stiffness. You hit the peak stress, and in this regime, you see more unstable crack growth. So often, even if we were to unload the material, it's already done. Those cracks are still taking off. The advantage to the Kolsky bar test is we can get up to strain rates of like 10 to the third, 10 to the fourth per second. I didn't make this clear before, but we're looking at applications typically at high rates, so we're particularly interested in rate effects. So the basic model, what are the capabilities? It's a damage-based stress-strain relationship, so it's handling crack-related damage. It doesn't handle other mechanisms that might come into play, amorphization, phase changes, melting, shear banding, I don't know, crystal plasticity. None of that is at play here. So we're only handling this one mechanism. We'll incorporate both initial pore-like and slit-like flaws. So we'll take anything that kind of is a chunk of something or a bubble. We'll say it's kind of like a circle. Anything that is some sort of flat kind of structure, we'll say is like a straight line. So again, it's an idealized geometry. But for each of those, there's a number density, so the number of those flaws that occur per unit area, because this is a 2D model. We have a 3D model as well. There's a size distribution, so the percentage of flaws of different sizes. And in the case of the slit-like flaws, an orientation distribution. So what orientation are they relative to the loading? And the model does incorporate strain rate effects. So it turns out at high strain rates, you have a higher apparent strength than you have at low strain rates. And it has to do with how the flaws are, how cracks grow from the flaws under different rate conditions. I'll try to touch on that in a little bit when I show you the results. And we can handle a multi-axial stress state, so we can handle confinement. But for here, I'll stick to uniaxial, again, just to kind of get you on board with what the model is doing basically. So here's how it works. So we're producing the stress versus strain for a fixed strain rate, and we're doing a stepwise solution in time to do this. And you could imagine if this was operating at a particular integration point of a finite element model, what each one of these time steps would be a load step at the larger scale. So the larger scale model would call down and would say, okay, the strain's increased by this much, what's the new stress and damage level, and then go back up. But for now, we're just using the constitutive model, so we're just looping through time uniformly. And so the first step is we have a global stress. We'd like to know what is the local stress. So it turns out the stress on an individual flaw is not the same as the stress on the whole sample. There are localizations that happen because of interactions between these cracks. So how we approximate that interaction, and it's approximate, so we're not capturing the direct, if you have two crack tips some distance from each other that are very close, we don't capture the direct influence of their stress fields. But what we do capture is sort of a net interaction from softening of the surrounding material. And this is in a self-consistent model. So basically think of, here I drew a porous material. So you have these pores, and the cracks are developing from each of the pores under this compressive load. And we take any individual pore and say that the material around that particular pore and its associated crack is pristine. It's undamaged. But everywhere else is damaged, representative of all the damage of all the other pores. Okay. So this boils down to basically an elasticity solution. You have an effective modulus or moduli, it's actually anisotropic damage, that represents the stiffness of the material out here that's different than the pristine stiffness. And from that, we can figure out what the local stress state is approximately for each of the flaws. So the next step is once we have those local stresses, it's pretty straightforward to come up with a stress intensity factor. So we used a classic Horian-Niemann-Nasser solution for a wing crack under a given stress state to find the stress intensity at this crack tip, and we're just dealing with mode 1 stress intensity. As long as this crack length is long enough, it doesn't have to be very long at all, longer than maybe ballpark 30% of the flaw size, then that mode 2 that mode 2 stress intensity is not terribly important. So we're not throwing away an awful lot there. And so it turns out to be this kind of function. Sigma 2,2 and tau are associated with the stress state. Phi is associated with the orientation of the flaw. L is the crack length. S is the original flaw size. So you can see this sort of classical standard solution that you probably know from simple LEFM. And then there's this other factor that accounts for the sliding forces on that flaw surface. So with the stress intensity in hand, we'd like to figure out what the crack lengths, how the crack lengths have evolved in that load step. So how we do that is we use this, this notion that the crack growth speed is not infinite. The crack growth speed is rate limited. And we assume that, for lack of much better information, that it's rate limited by the Rayleigh wave speed. There are these parameters alpha and gamma that sort of temper that wave speed, that Rayleigh wave speed, but in most of the analyses we usually assume alpha and gamma are 1. But there are some data that suggest this might be something like 1.5, and this might be something like in the 0.3 to 0.7 range for different materials. But it's not, they're not well characterized, so we kind of stick with 1 as to take them out of the equation as something that we're varying. And so what you see here is that as K1, the stress intensity, overstresses over the critical stress intensity, or the mode 1 fracture toughness, that crack growth speed increases. So it's increasing with an increase in the overstress, in a sense. Now this change in crack length feeds into, this is our damage here, our damage measure. Again, I'm presenting a very simple version of damage. That is, eta is the flaw density, so it makes sense. The damage is associated with how many cracks there are, and it's linearly related to that. L is the crack length associated with family J, so we could have multiple different crack families that we're tracking, and we look at how much the crack length changes in that family. And then this G delta A is just the probability that any particular flaw lives within that family. Okay, so it's like a weighted average of your crack length squared. And you can also calculate damage rate and use that to get damage, or just go to damage directly from your crack length. And just to give you a sense of typical flaw size distribution is something like this. This is actually something we measured for the pores in the air-entrained mortar, but it matches with a lot of other data that's been generated by, like Jim McCauley has some data for ceramics that suggests the same kind of thing, a sort of power law distribution in initial flaw size. So there are many small flaws and very few large flaws. And we'll talk about that later. So the next thing we do is take that new damage, figure out an effective modulus, and use that to calculate our global stress. Then we're done. We can go to the next step. So again, a simple model just for argument here is a Budiansky and O'Connell model that assumes an isotropic, a fully isotropic material. Actually, we found it's not. It's an anisotropic material, and we have an update to this, but I could spend another 45 minutes talking about the anisotropic model. So for now, think of the elastic modulus degrades with damage, somehow with a function of the Poisson's ratio. And we kept the Poisson's ratio constant in this particular analysis, just to keep it simple. And so you can get your global stress. Now, this is what's different in these rate-dependent problems. In classical static problems, you think of, well, your stress rate or your stress increment is just your constitutive properties times your strain rate. But now we actually have a degradation of stiffness, so there's a second term that pops in there that's a rate of change of the stiffness times the strain. And so you can, from that, calculate your new stress. This is the reason we have to use a finite difference kind of approach to solve the problem. And then now we're done, ready to go back and do the analysis again at the next load step. So let's show this for air-entrained mortar. The reason we chose air-entrained mortar is because we could make a sample that was small enough to be a representative volume to fit into our Kolsky bar. So we needed nothing, it couldn't be anything bigger than about 1.5 centimeters on any side. So we needed to have that be sort of statistically representative somewhat of what the material would look like. So concrete was out, full-on concrete. This wasn't going to be a good size sample. But we put the air entrainment in there because we wanted to have some nice, easily characterized flaws that are introduced sort of intentionally that we could easily see and define the distribution of them. So we're not defending air-entrained mortar as a something that you should use for anything in reality. You're welcome to, but it really was truly for us a model material. And this was done with Kim Curtis at Georgia Tech. As I say, it was kind of a useful model material. We used serial slices to evaluate the pore size distribution. So we conceptualized this air-entrained mortar as having as a material that has two types of flaws, the pores and these slits. And those flaws will propagate cracks, but at different local stresses. But both flaw types contribute to the overall damage. So you just kind of add together the contributions of all of them to damage. And again, this is the distribution that, from characterization that we found in the radius of the air-entrained pores. We had to do a little bit of hand-wavy kind of stuff for coming up with slit flaw population. So what we said is, well, we know that the ITZ, the interfacial transition zone, is a weak area in a concrete-like material or in a mortar. So what we did was we looked at the distribution of sand grain sizes. We sieved the sand before mixing it in. And then said that, I don't know, we'll ballpark say about the radius of this sand size is maybe about the size of what we consider to be an equivalent slit size, a slit flaw, crack-like flaw. It's an approximation, but at least it gets us to the right length scales. And here's what happened. When we put these into our model, we get different samples. So these are Vinsol and wood were two different entrainment agents. There was really no difference between them. Don't worry about that. So these are really just labels for our 8 different samples. And we ran them through the model and came up with the stress strain results. Please, I hope this isn't too much of an eye test. I will point out the most important things. But for each, there is a particular flaw density. This is the number density of pores, total porosity, the mean pore radius and maximum pore radius for that sample. So we were able to read all of these from the characterization. And then we predicted strength for each one. And what's interesting are a couple things. Strength is related to the number density of flaws, or the porosity. But that's not really the whole story, right? Because these two samples had the exact same predicted strength, or close to it. But they have somewhat different porosities and somewhat different density of flaws. Strength relates to mean flaw size, true. So if you look through here and you look at the mean flaw size, a higher mean seems to correlate somewhat to a lower strength. But again, it's not the full story. The weakest sample has a smaller mean flaw size than the second weakest. So it's not 100% correlated. The strength does relate to the largest flaw size, but again, it's not the full story. This one has the largest flaw size, but it is stronger than this other one that had a smaller, large flaw size. So there's this complex interplay between the population of flaws, not just the number of them or the size of the average or the size of the biggest. It's kind of all of these together that are important. So, I'm sorry, let me go back here. Last thing I forgot to point out, the Kolsky bar test gave us a strength of around 85 MPa. Our model's over-predicting that, but it's not over-predicting it horribly. It's actually pretty good. We didn't do any parameter tuning here. We didn't, tweak alpha and gamma to get it to match or anything like that. We really went in blind and used the model and saw how we did. And also keep in mind, this model only captures one failure mechanism. It's only brittle crack growth. It's not incorporating anything else. So again, no parameter tuning. The possible errors, there might be some other mechanisms going on here that we didn't capture at all. We didn't think about the fact that these cracks coalesce and that further weakens the material more quickly. We're just dealing with individual cracks at this point. This is a 2D analysis. Actually, the 3D analysis, it turns out, came out about the same. So, but you know, there are possibilities here for problems. But it is based on the underlying flaw population and the rate. And why that's important is, remember back to our cartoon at the beginning, said there's a finite element. Each finite element has its own underlying microstructure. We now have something that could potentially link the microstructure description to the constitutive properties, and it's not a sort of ad hoc effective properties kind of link. It actually explicitly tracks the microstructure. But we don't have to do that horrible cohesive zone model that had all the cracks explicit in it. So it's still costly at every integration point. And our question is, can we simplify this? So I'll get to the next issue we thought about. So remember when I described the crack families, there was, if you think about the flaw family, or the flaw population, we had binned them into sort of representative families, and you figured out how much should each of those bins, how much should the associated cracks for each of those bins grow. So you could imagine that the more bins you have, the more accurate you are. But the more bins you have to multiply that by the number of integration points in your large-scale model and do that many more analyses. So you really want to scale back the bins as much as possible in order to be able to implement this in a large-scale analysis. So how do we do this in an optimal way without reducing the accuracy? So this was something that we started thinking about. So again, the inputs varying between integration points in a model like this. We want to minimize the amount of information we have to track at each of those integration points. So think again of, we're looking at flaw family. So here's a flaw population at a very large scale, and you have some specified distribution, a Pareto distribution maybe. When we take subsamples, though, you have significant sampling error that arises. So as your finite element gets smaller and smaller, you have more and more of this sampling error. We also have more and more variability from sample to sample. Do we want to calculate or deal with every single one of these bins? That's a pretty huge number of bins. Or can we capture this variability quite well using a small number of bins? So again, just this is demonstrating for you that sampling error. As I go from one sample to another, I get significant differences in my effective stress strain curves. So this is the situation that we're in. We already talked about the fact that we can't go out to infinity. So infinity was like a finite element bigger than thousands of kilometers squared. That's off the table. That's not true. We know variability matters. We could have a finite element mesh that's sort of down at this scale, where there's maybe 1 to 10 flaws per element. The problem is that damage assumption is probably not a good representation of that element anymore. So what does it mean to have damage of a flaw population of 1? It's kind of a weird, if you're down to that scale, you should be using a model that actually explicitly models each crack. So then you're in the domain. I feel sorry for you. That's hard. We're kind of in this region. Okay, so we can't go to infinity, but we do have a large crack population in each element. And this is just too large to track each of those cracks individually. So we need to bin them into little groups or families. Oh, so our question is, we have this damage that really is a weighted average of all the crack lengths squared. So LP, or each sample crack, what its length is. Could we represent this instead by something that's a weighted average of crack length squared over a very small number of bins? So in other words, the number of bins should be much less than the number of cracks in the population. We'll save ourselves a lot of effort if we can do that. So then I started asking mathematical questions. How does this work? What's going to go? So this is what I'll show you, is how we came up with some logic for this. So we'll step back for a second and say, well, get out of the world of cracks. So if I've totally lost you and bored you on brittle dynamic failure, here's a good place to turn your brain on, step back in, and just say, okay, I'm going to look at some math for a while. So think of any generic function. We call it h bar. That's some sort of average over some evaluations. So LP and theta p, for example, are just some random variables. So this is a sum of a generic function of random samples. So you can think about it as voting numbers or any random sample you like to think about. So our question is, can we identify something that's an accurate approach that takes this summation over Pmax, which should be a very large number, and breaks it down to this, which should be over a much smaller number? Because then we have to do many fewer evaluations of H, and that gets costly if we have too many. So our question is two parts. What should be this weighting for each of the bins? And where should those bins be located in the sort of sample space? So just for example, let's say we decided that our random number, our crack length, for example, is coming from an exponential distribution. Well, an exponential distribution is defined on 0 to infinity. How am I going to bin that top bin? So the first 9 bins, no big deal. I can say from 0 to 10, or 10 to 20. But all of a sudden I get to this point, I've got a bin from some number up to infinity. Where's the center of that bin? What's the representative value for that bin? So this is an awkward process. Or you can say, well, I'm just going to decide there's a big value, that's the reasonable limit on how large something can be. That's fine, but tell me what that value is. And your answer will be sensitive to what you choose. So instead, we started thinking about probability space. Oh, probability. But it's not so bad. Just think of it this way. This is the probability that a given, well, crack length in this case, is less than the value L0. So I can just take this function and swap it around. And I can say, what's the crack length associated with a given probability? That's fine. So what crack length is such that 99% of cracks are smaller than this value? And that R1 is the 99.99. So what this does for us is it gives us a mapping. Think about in probability space, no matter what distribution I sample from, those samples will always be sort of uniformly distributed across probability space. It's in the mapping that I capture the non-uniformity. So over here, I'm sampling, let's say, in crack length space. So this is crack length and orientation, for example. You can see that I'm capturing many small flaws and very few large flaws. But in this space, it's totally uniformly distributed. And what's wonderful about this space is it goes from 0 to 1. It doesn't go to 0 to infinity. So it gives me a nice mapping back to the 0 infinity space. So we're back to this function here. Think of this as now being something that, we're taking an average here. So when you take the average of something, the mean of something, it's the function times the probability density function describing it. So this summation is approximately the function h integrated times the probability density function of those variables. Where, in this case, that probability density function is simply a bunch of Dirac delta functions. So these are identical terms. Just think of this PDF here as a bunch of deltas. Everywhere there's a sample, there's a delta spike. If we transform that to R space, we get the same thing, except now these spikes are in probability space. So how does this work? In 1D, you're going to, at the end of this, say, this is really silly because you had more bins than you have samples. But in reality, imagine I had a huge number of samples. But right now, for demonstration, I just have these 3 sample values. And I'm working in the R space, but you can imagine that's going from 0 to infinity or whatever variable I have. So the first thing we do, we'll just say, let's say we bin this, divide this into evenly spaced cells. They could be uneven too, but just for the sake of argument. And what we'll do then is say for each of these, we're going to map over to the edges of those cells, the nodes, some power associated with that sample. So these are these red lines now. So we've taken these delta functions that were here and sort of moved them over to the edges of the cells. And then the next step is to take those nodal values and put sort of a delta-like function there. So put a basically a shape function there. And then we can add all of those together. And so what we're saying is this green function is sort of an approximation to these three delta functions. It looks awful because I only had 3 samples to start with, and that was so simple. But I just want you to see the basic concept. And so this is the same function again. And what we do then is use Gauss quadrature to integrate under this function. Okay. So we take, this is just 1-point quadrature. At the center of each of these cells, we put a Gauss point, and we assign the weight to that Gauss point based on the Gauss quadrature parameters and this green function here. So again, let's start from the beginning. These were the original samples. They're now being approximated by these red samples. Now, if I had 10,000 of these green samples and only 10 of these, it would give you a much better sense that we're actually representing something realistic here. This was an admittedly cartoon version of this. So this is the exact. This is the approximate. The bin locations then are fixed at Gauss points in the probability space. The weights are affected by the sampling variability. So from one sample to the next, you will have different weights at those Gauss points. And you have more bins than cracks with this, but with a large number of samples, you can have many fewer bins and do a very good job to represent that large population of cracks. You could also do a non-uniform grid in the probability space if you have reason to believe that that will get you further, and we do, but we'll get to that in a minute. But the same concept holds. So what you really need to know in order to do the zooming is just what is the objective you're hoping for when you do this binning. So here's an example where you could say, well, if I'm really, for example, in damage, the large cracks dictate quite a higher proportion of the damage than the small cracks. So one might say, well, I'm happy to just sort of have a large bin that represents all these small cracks because who cares about them anyways? But I'd really like to discretize well out here. And so here's a simple comparison of just some sample CDFs that we just generated, random number generation. And what I'm showing you here are the green are the cumulative density function. This is, again, the probability as a function of the crack length size. So the green is based on the exact solution, the exact sample. The black is based on a bin solution. You know, it's not so great. We went from 100 points down to 32 bins. So it's not so exciting, but it shows you at least that they do converge to the same thing. And here we use zooming because we say, well, over here maybe we care more about the large cracks. The error here may not be important. And if we look at the mean square of crack length, you can see that zooming actually brought the error way down. I'll get back to mechanics in a second. So if the second part has got you feeling like you missed mechanics land, we'll be there. So then the last thing I'll just point out, we're getting back to binning. So think about those cracks. We had to bin them into families. So if you were sitting down and I said, I want you to take a population of cracks and put them into representative bins, you're probably most likely, and I did this for a long time, to just say, well, I'll break them into equal crack length intervals. And that's fine. You can do that. You do have to set some upper limit on how large the cracks can be, but you can do that. Or you might say, you know what, I want each bin to have the same number of cracks on average. So you can do that too. That's what this one is. So see, the increment in probability is the same as I move up, but it's uneven, of course, in this direction. Or, if you wanted to, you could do something in between. And that's what we did here. Actually, what we did here was we wanted each of the bins to contribute equally to the total damage. So remember that damage function is like a summation of square of crack length. So we wanted, and that it also depended on the number of flaws in that bin. So we went to equal damage. It's kind of smaller bins, it's distributed across. And then there's a notion of a crack evolution. So we bin them. We have a population of flaws. We sort them into however many bins, right? Then the next thing we do is we run it through the micromechanics model. Each one of those bins, this bin, the cracks grow a little bit. This bin, the cracks grow a lot. This one, they grow sort of a medium amount. But we need to keep tracking that. And so there's this sort of notion that the cracks evolve as we're loading. So the bins are sort of, the bins themselves, a crack doesn't move from bin to bin, but the bin itself is evolving in crack length space. So there's a growth model that takes us from the initial characterization out. The micromechanics model is what tells us how those cracks will grow. And the damage associated with the bin evolves. And after loading, then we have a group of cracks now with a new length and maybe a new orientation. So this is where the rubber hits the road. So this is really the punchline if you didn't follow the rest of it. We had 10 to the 4th cracks. We put those 10 to the 4th cracks into our micromechanics model, represented each one of them individually. And that is this red curve right here, the stress versus strain predicted from the model for that. Now, I think it's the black. I think this might be incorrect, this legend. I'm sorry. I think it's the darker of the two. Doesn't matter much. Now, then we took the cracks that were binned into equal intervals of crack length. This is the blue curve. And we made 10 bins. And the results are not too satisfactory. We're over, I don't know, about 20% error. Then we did 10 bins with an equal number of cracks per bin on average. And we get this green curve up here. It's better. I don't know, what is that, 5%, 5 to 10%? But it's still not great. But then we took 10 bins where we had binned them according to equal contribution to initial damage. And wow, that's pretty nice. And we went from 10,000 cracks that we had to track down to 10 bins that we had to track. Basically 10 cracks that we had to track. So we cut out 3 orders of magnitude just by binning with minimal loss of accuracy. This is just a plot of the error as a function of the number of bins. Basically, that's what number of elements means. We should have said number of bins there. And we see, again, that the equal damage binning exhibits lower error. So by being clever about how we binned, we saved about another order of magnitude. So binning alone saved us 2 or 3 orders of magnitude, actually 3 orders of magnitude in this case. Binning well saved us another order of magnitude. So it wasn't that hard. It didn't take much for us to think about this, but coming up with the construct around it actually took quite a bit of time. So again, simple binning is very useful. Clever binning is even more useful, and it doesn't add anything to your computational effort. It's just something you establish up front. Our last question is if we can further simplify the model implementation at each integration point, looking at typical, think about typical constitutive models. You don't necessarily track a crack at every load step, but you have some sort of stress versus strain relationship. And this is a short section. So we're at this last, the transfer method. And this is a fairly simple concept. actually, it's so simple that I would like somebody to tell me if it's been done or where I should look to find similar work. Because it really is a relatively new idea that we're just thinking about a little bit. So we're given a load step at each integration point. We are trying to figure out output, new crack length, stress, and damage. So we can do this at every integration point. You have its own crack population, and you're tracking the cracks there, and here a different population, and here a different population. But we started thinking, you know, they're not all that different than each other. These all have kind of the same shape. We're reflecting the same physics. And so what we thought about was, why don't we just do one run, stress versus strain, then figure out in that one run what the gradients are with respect to the things that change from one integration point to the next, and just use a Taylor series approximation to the results. So basically what we're doing is we're only calculating global damage at every integration point because we have the gradients from this sort of reference run. So we're doing a perturbation kind of analysis. I think of it as a reduced order model or a surrogate model. So again, you have this initial analysis where you calculate sort of a reference damage, crack length, and gradient of crack length at each load step. So then in a given integration point, you find your reference damage based on the strain. You update the damage based on perturbations in your flaw population. And then you calculate your stress and move on. So you don't have to do any micromechanics analysis except for the first one that you did, the reference run. And so here's a quick analysis that we did where here's a reference PDF of a flaw size distribution. And we perturbed it. We perturbed it pretty significantly. So the yellow is just some perturbed sample of flaw size distribution. And over here, these are the results. The blue is the result from this blue initial curve, the reference run. The green is taking this perturbed solution and rerunning the whole micromechanics model. Overlaid on top of that is the red. That was run using this transfer method, just this perturbation. And it saved 100 times. So we'll cut way down on our computations. And it looks here like it only works for small perturbations, but we perturbed a lot of different properties, and we're able to get really good results, again, with quite a bit of savings. I think this is reduced order modeling or surrogate modeling, but if anybody really knows this area well, love to hear it. So I'll tie things up. The punchline is random local heterogeneities are associated with failure. We have to deal with them. The finite element, each of them we can think of having its own associated underlying structure, lower scale structure. You could do a lower scale analysis for each finite element, but it quickly you start asking the question, well, why didn't I just do a huge finite element model that has all of the microstructure in it? Instead, we try to use a reduced order representation, and the examples I gave here, typically for brittle dynamic failure, cutting down the number of microstructure parameters that you have to represent. So binning cracks is that you can think of that as a parameterization, or thinking cleverly about how you develop gradients and maybe can you use those whenever possible. And we're currently applying this to material point method models. And a student that I worked with KT Ramesh, who just defended last year, this is his material point method MPM model looking at spherical impact. And he was looking at sort of the effect of rate on the damage distribution. So you see that as the sphere hits this cylinder faster, you get a much more dispersed damage pattern, which matches our experiments. And I think that is it. So we're well on our way to fun models now.
So let's open for questions. Questions? Yes.
Do you have any of your little cracks that are unstable? So you seem to imply that all these cracks
They
grow in a stable manner?
They're actually growing unstably, but they're rate limited. So they're not able to reach their equilibrium length. So they're taking off, but they can't take off at infinite speed. And what's happening at these high rates is the loading is happening so fast that the crack length doesn't have time to catch up. So it is, in a sense, unstable crack growth, but the fact that it can only happen at a finite speed keeps that from becoming a problem for us. Yeah.
Sorry, go ahead.
Then how you had strength, of course, identified as this peak stress. So what are the conditions then for your cracks at that peak stress? Because all those conditions were always initial, correct? So when you identified, a certain flaw density or porosity, that was initial.
Yes. And so, but for each of those families, you have this crack growth that's continuing. It's interesting, there's not really there's not a switch that, I would have expected at that peak stress you would see some switch that happens, like suddenly the cracks are doing this. And it's not. It's literally the point at which the deterioration of stiffness outweighs the increase in the strain rate. But there's not like a physical watershed that, suddenly everything's changed. But the individual, I feel like I'm not answering your question. So
this rate effect has to be there to get that.
So where the rate effect comes into play is under static loads, the big flaws tend to dictate what the strength is. So if you have a large flaw, the crack takes off, it's unstable, the sample's done. When you load it quickly, what happens is those big flaws activate cracks first, but those cracks are growing at this speed, and the load is cranking down on them. So then you have other little cracks over here, and they start to grow, and this one starts to grow. So you excite the whole flaw population at high rates. And so that's why you get this more dispersed damage. So that's where the rate effect comes in which parts of the flaw population actually exhibit damage. And it's exactly what we see. So you have a good point. We do have unstable crack growth, but this big flaw is undergoing unstable crack growth, but it's rate limited. And because of that rate limitation, it's allowing these other flaws to start taking off too. And you see the damage as a function of flaw size. For static case, it's like all in the big cracks. If you were to look at how damage distributes with flaw size for the high rate cases, it's kind of an even across the board kind of. Those small cracks matter too. So it's the number of cracks is more important at high rates than the size of the cracks.
I think I'm the next. So you're using micromechanics. That means that you imply that your material is statistically homogeneous. So on this micro scale, you have to have representative volume element, and it raises the question of its size. So how you address it in your model?
So I guess I don't know that at the lower scale, I think we don't have a representative volume element because we do have this variability from one region to the next. So it's not truly representative of the full microstructure. What we're doing right now is, in a sense, you think of it as at the large scale, you have this element on which you determine what the local stress and strain are. Those define the boundary condition on this sub-RVE scale sample that the element represents, but it's not really a representative volume element. So in the micromechanics model, what we're doing is we're taking an input stress and strain and trying to predict an increment of stress. But we're not using anything like a periodic boundary condition or the kind of thing that you would need if you were truly using an RVE kind of approach.
In your simulation of mortar, how did you selected K1C and
Yeah.
Young's modulus of non-damaged material.
Yeah, so K1C, let me think about this. K1C, we weren't able to figure out a dynamic stress intensity, so we didn't use a dynamic value. We just used the static K1C. I can't remember exactly where in the literature we pulled that out, but we pulled it out for cement paste because we assumed that most of the cracking would travel through the cement paste and not through the sand aggregates.
But that's but it's usually already entrained cement. So how do you take that out?
So the air entrainment, it's assuming that if we get down to the scale of the regions of cement paste that are between those air entrained pores, that is the mode 1 fracture toughness of that small piece of material. You know, but we didn't have anything better for what a subscale fracture toughness might be. So for lack of better information, we took the macroscale value. But we used cement paste and assumed that the interaction with pores and with other pieces of sand, we're ignoring that.
And the second question is kind of related to previous question. If you perform a simulation, will you be able to simulate a size effect? So if you run it on a larger specimen.
That's a really good question, actually. We haven't looked at it and tried to do that yet. But I think it's actually something that would be really interesting to probe into to see if... My sense of the size effect is that there's a piece of it that's the statistical problem. And of course, I'm here with John Lang, right, who can correct me in a second on this. But that's a piece of it, but it doesn't answer the whole question of the size effect. And I think there's a boundary condition effect that comes into a play there as well. But it would be interesting to probe that. So we're just at the point where we're starting to get to those larger, the next scale model where we could start to play with some of these things. So it's a really good thought.
Okay. When I was watching your binning, which I understood better than mechanics, it looked like you were doing something like a Metropolis Hastings Markov chain Monte Carlo approach of importance sampling.
Importance sampling, yeah.
Is that essentially what you were doing, or am I missing something?
No, I think that's exactly right. I think it's a specific form of importance sampling. So you set the importance sampling based on, in this case, the damage that you're trying to use to represent that that flaw population. So yeah.
Okay, I think we should end here and let's speak again.
Thank you.